So today I'm going to talk about different stuff in computing that I remember without any preparations. So I decided to talk a little about what the program, the application that you run on your computer looks in, I don't know, some abstract representation maybe. So operating system is a huge program, and it runs inside your computer, and it's the first program that starts when you power on your computer, and this is the last program that finishes when you power off your computer. Of course, according to Linux, there is a core for the operation system, the core which was written by some programmers, and there are additional resources like drivers which help your core communicate to the physical devices like keyboard, mouse, a keyboard, a mouse, maybe a printer, something like I don't know, disc recorder when it was in early versions of computers. Before there are only USB ports in the modern computers. Yes, all this stuff, and the core of the operation system and the drivers create this environment inside your computer where you can run different programs like Word, the Microsoft Word, PDF reader, a browser, some video something to watch video, some video player, maybe games and other stuff. And in general, when you start each particular program like a calculator on your operating system, this program lives in some abstract space. This way, this program occupies some memory inside the computer, inside the operating system, but from the point of view of this particular program, there is only one plain memory space, and it has it consists of bytes in memory, and all these bytes have numbers from 0 to FFF. I don't know. I don't know how many. Maybe 2 gigabytes, 4 gigabytes in 32-bit operating system, and up to, I don't know, 64 gigabytes in 64-bit operating system. And so this memory, this abstract memory, can be represented as a long road, let's say a long road, and in the beginning of the road there are addresses, memory addresses with 0, 1, 2, and so on, and in the end of the road these maximum numbers like FFF, which is, and all the numbers are in the hex, I don't know the correct word, hexadecimal, hexadecimal something. The way to count numbers, not by tens but by 16s, yeah, as a base of something. So the program usually occupies the space for the 32-bit operating system. The program usually occupies the space with the addresses from 400,000 in hexes and up to the larger numbers until the whole size of the program will fit, or just fits into the memory space. And in this memory space at higher addresses there are libraries which are DLLs, like kernel 32, user 32, and other libraries that were loaded by the program, because this particular program uses the functionality from these libraries. And I think somewhere in this memory space there is heap, for which is the memory, some random memory where the objects that are created in this program are stored. The objects are stored in the heap during the operation of this program, and there is a stack where the frames for the functions which are called during the operation of the program are stored. So in the stack the frames of the function are stored. In the heap the objects are stored. All of them are created during the execution of the program. So the interesting thing that all this memory space is abstract, because it's much huger than the real operating memory that is installed inside the computer, and somehow the operating system creates this illusion of this continuous memory space for each of the programs that that exist inside the operating system for this particular moment. So let's say there are 50 programs running simultaneously inside the operating system. So to get the whole space, memory space that is used by all these programs in the terms of all this continuous memory space, we need to multiply these 50 programs by I don't know, 4 gigabytes of this plain memory space, and it will be huge numbers of memory which are unrealistic for every personal computer to have installed. Yeah, but everything works fine because lots of this memory space in this plain memory space exists. Lots of the space exists only virtually. Somehow a memory management of the operating system finds the way to make the particular program think that this program is the only one working. This program is the one using all this memory, yeah. But all this I don't know particular details. Somewhere 10 years ago maybe I read in Rusinovich about this process of using some pages or swapping to create this illusion of continuous memory space, but I never used it even for programming purposes, so it was just a theory for me, and I never retold it to someone, so I just forgot about it, and now I remember what I remember. But about this mapping from the real modules of memory installed in the computer to this plain continuous memory space. But an interesting thing that when I debug some programs in debuggers like Oli Debugger or an Oli Debugger or an XDBG, the debugger shows this plain continuous memory space because the debugger looks at the memory from the point of view of the particular program that is debugged by this debugger, and the debugger has several sub-windows, like the main window where the assembly instructions are shown for each memory address of this program, and in this particular in this main window all the bytes at different different memory addresses are interpreted into assembly commands, so that you can read these commands and understand what the program does on this assembly level. There is another sub-window, which is the dump. The dump view, and it shows this bytes in hex way, not interpreted into assembly instructions, but in hex way, like A1, F, 0, 3, E, and so on. And at the same time, the bytes that can be translated into the strings are shown next to these hex representations. Yeah, and sometimes it's kind of convenient to see that some bytes at some memory address create some readable string, which is readable for human. Yeah, and other two sub-windows are for the registers and for the stack. And registers are the things that are used by the central processor unit to perform all these assembly instructions, take bytes from the memory. The CPU takes bytes from the memory, then it performs operations, arithmetic operations in the registers, and put the bytes back into memory. And all these registers are used to perform these operations in a very quickly way. Yeah, so this is just the way the architecture of the personal computer works. So there are these registers like AX, BX, CX, DX, and other registers, and there is of course IP, instruction pointer, which points to the current position, to the current instruction which in the memory, which is performed by the debugger, for example. And SP, stack pointer, which points to the top of the stack. And the fourth sub-window in the debugger, which is shown, is the stack itself. And dump view, it's more about watching the heap, and the stack is more about watching the stack, but the stack works mostly with the frames of functions. So actually I think that the main view and the dump, the main view with the assembly instructions and the dump view can show you the information for each other and for the stack, but this information will be represented in very inconvenient way. So all three sub-windows are made to be convenient to look at some particular areas in the memory space of the application. And the fourth windows, which is about registers, can be displayed in other sub-windows. It's like a locked sub-window. Well, it's kind of a difficult concept if you never saw these types of representation of bytes of the program, and it's even difficult to describe it without watching at any working debugger, just from my memory. But it's quite an interesting topic in general. And to understand what you see in the debugger, you need to know these concepts of the continuous plane memory, the concept of assembly instructions, which is the low-level representation of almost any computer program that can be run on particular processor, then you need to understand the idea of stack, heap, and registers. Without it, you will look at this debugger with the windows and you won't understand what is going on. Even when I transition from 32-bit programs to the 44-bit programs, lots of the things is different because the stack, the heap are different, and the registers are different as well. And though they are the same concepts, just with just different size and other attributes, it's very difficult to adopt to the debugging of 74-bit program after you spend a lot of time in debugging 32-bit program. So I can understand how difficult it is to just start learning this idea of debugging a program, in Windows, for example. And there are also other types of tools that you can use to reverse the program, which are decompilers. And the best decompiler for C++ programs is Ada Decompiler. When you put the program into Ada Decompiler, after processing this program, you get the same plain memory space that is shown in the first subwindow of the debugger. But because I either decompiled all the program and processed all the program beforehand, before showing you this memory space, you can make different searches inside of this program, find the different connections between functions to which you can jump from somewhere, or from which you can jump somewhere else. And if you click the specific keys on the keyboard, the ADA divides and shows you this plain memory space in the way of logical blocks, like the body of the function, the body of the cycle, and all these logical blocks are connected to each other by these jump instructions. And by these jump instructions, and with this representation of blocks, it's much easier for you to understand what's going on, because your brain can't get the whole picture of these jumps from just the plain continuous memory space. In the debugger, the similar option was added, but debugger is not so clever in this particular thing, and when you create the diagram with these blocks, you can get hundreds of connections between small elements, between small blocks of code, especially when these connections are created by getting some value from from AX register to make these jumps, which are just unconditional jumps. When you use the value of the register plus some value, then changing this register, you can make jump to different parts of the code, and the debugger can't interpret these jumps, and it creates dozens of jumps to the possible destinations. But either Decompiler can understand these jumps, because these calculated jumps usually point to two different places in the code, and this graph representation of blocks and jumps between them in the IDA is less stuffed with different arrows and some potential jumps which will never be performed as the debugger shows, by mistake. And the next feature of this decompiler, that when you press another special key on the keyboard, the IDA tries to restore the C++ code from this assembly representation, and some programs can fool the IDA decompiler by performing the operations on the stack, and this way IDA can't show you the correct C++ representation of this particular code. So you can't really hope to rely on the IDA decompiler on 100%, but sometimes it's quite a useful feature that you can use, and there is an option to add WinDBG or QEMU debugger inside this IDA decompiler, and then you can switch between these two modes and debug the program, and then decompile or show the assembly code at some point using this graphs and jumps diagram. It's useful when the program decodes itself during its execution, and at the start of this program the IDA decompiler couldn't show you the right graph representation of the code that will be decoded somewhere in the middle or in the end of this particular program. But I prefer to work with the pair of programs, the XDBG, the debugger program, and the IDA, which is the decompiler program. They are not connected the way the IDA can be connected to the WinDBG or QEMU, but that's quite alright for me to debug the program in this XDBG thing, and then to create the graph representation in the IDA for the particular space, for the particular places of the program where I need it. And to do this, I can for the program that modifies itself during the execution, at the point where I am interested in this graphs representation, I can stop the execution, the debugging of the program in the debugger, and then save the memory representation of this program from the debugger to the hard drive, and then use this saved memory representation inside the IDA decompiler to get the graphs that exist inside within this particular at this particular moment of the execution of the program. So the combination of these two tools is quite convenient for me. Well, I think this is all what I wanted to say about the debugger and the decompiler for today, because it's quite a difficult topic, and because I wasn't prepared for it, or I didn't created some lecture beforehand, so I came with explanation from my memory, from my understanding, and it was really difficult because I needed to remember what happened inside these two programs. It wasn't just the description of some ideas that I had in my head, it was the thinking about the particular stuff that exists without connections that exists independently of my own ideas. So I had to be correct with it, and I remembered all the stuff on the go. And in the end of this lecture, I want to talk about more simple stuff like anime and the way the blood is depicted in different animes. So in this Chainsaw Man, huge hit, anime huge hit, the guy Denji, he fought against demons, demons, and he kills them because he's a demon hunter, and this is his work. And all these demons have different forms. Like there are big bad demons, or there are, I don't know, monsters with different shapes, like huge head with lots of arms instead of legs. Or there are the human-like demons, which are the Chainsaw Man himself, who are Chainsaw Man himself, or Katana or Blade Man as well. So when the demons are cut into pieces, they have the intestines and other stuff inside the guts, which is similar to the stuff in the guts of the animals, but their blood is always green or blue or violet, and this is kind of strange for me. But the blood of these human-like demons, Chainsaw Man, Blade Man, their blood is always red because they are partly human. So I don't like this concept of depicting blood in Chainsaw Man. But in other animes like Kaiju number 8, where the different teams of warriors fight against huge kaijus and smaller monsters. All of these kaijus have red blood, and of course they have lots of, I don't know, intestines inside the guts. So when this Mina warrior shoots this kaiju monsters with her huge gun. There are usually lots of blood out of that I don't know, pours out of the holes in the body after they are shot, but by the gun. But when this Kaiju 9 guy kills the monsters with one punch, these monsters kind of explode, and then all the blood falls from the sky with this bloody rain, and it looks really cool in the anime. And I think that if they did, if they changed the monsters, the color of the monster's blood to green or blue or violet, this bloody rain would not look so cool in anime. So I think this is the reason why all the kaiju have red blood inside of them, the way all the animals, all the humans and all the living creatures on the earth do. Yeah. So this was just a small notice about different types of representation of blood color in different animes. And this now it's more than 40 minutes of recording, so I stop with the recording for today.